Hey there, welcome to another video in the Learn APL with Neural Networks series. In this video we are going to implement the backpropagation algorithm so that our network can finally learn something. So how do we do that? Well, we essentially just have to implement the recursive definition of those formulas I showed you in the last video. And by the way, if you haven't, I highly recommend that you pause this video and watch 3 blue and browns videos that explain backpropagation really well. Those will be linked in the description. So pause the video now and go watch that if you want. Otherwise we will just keep moving. So what we will do is we will create this dyadic operator that we will call train. And what will this operator do? It's easy. Or, well, not easy, but it's simple to understand what it will do. It will take the constituents, so the things that make up a neural network, and also some derivatives of activation functions and loss functions, and etc. And for a given input, it will feed these inputs to the network, and then it will use these derivatives to train it so that the output produced by the network is or gets closer to the target value. And then by the time this operator is done, it returns the things that make up the network again. So this essentially looks like the header of a thread function, which I showed you in the previous video, except that this is going to be a thread op. So thread op for traditional operator, and the difference is here in these operands. Now, the first thing we do inside our dyadic operator is to split things in its parts. So for example, the network is going to be a vector with the weights and the biases, so we split that. And then the derivatives is actually going to contain the activation function and the loss function, so we split that derivatives. Now, because this is a thread op, much like in thread functions, we need to localize these names. So the activation function and the loss function. Now the next step is in actually propagating the input through the network. So we need to do the forward pass to compute the x's. And so the x's, how do we get them? Well, we take the network and we take the activation function and we give it to the forward pass along with the input. And this computes the x's. And now we can start computing the backpropagation algorithm. Now the thing we will do is, because we have our weight matrices and our bias vectors in vectors themselves, because that's the way the init network, or it's the way that we have built our networks, we will also gather all of the derivatives in vectors, and in the end we will use them to make small adjustments in the network. So the derivatives of the weights, and the derivatives of the bias vectors will start off as empty vectors. So let's go ahead and also localize these names. Now what we need to do is we need to start implementing the actual algorithm. Let me go ahead and show you. So it's not this, it's this thing over here. Let me show you the formulas from last time. The algorithm starts over here. So this is, you can call it kind of the base case. So this is how it starts. And then we just build upon it. And the naming that I will be using now is, I'll use the bottom part of this thing that looks like a fraction to identify the terms. So this is going to be called dx, then this is going to be db over here. This is going to also be dx and then dw. So we need these names, and we will also need names for these things over here, because our algorithm is going to traverse the network, and as we iterate through the network we need to refer to these things. So let's localize all of those names. So we need something for dx. We already have something for the dw's and for the db's. So there's dx, and then there's x, w, and b. Now what do we do? Well, we can start from the beginning, right? So what's the x? The x starts off as the derivative of the loss function. So the x is the derivative of the loss function, and that is computed by taking the target and using the derivative of the loss on the output of the network, which is that xn over here. But what's xn? Again, it's the output of the network, and that's the last value in our x's vector. So we take the last one. And now we use a for loop to iterate through all of the layers. How are we going to do that? Well, we need to iterate over the w's and the b's and the x's all at the same time. And so we actually use this in each, and so we need to iterate over the w's, the b's, and the x's. But now we already used one of the x's, we already used the last one, so we can actually drop the last one, so a -1 drop. And now it's the backpropagation algorithm because we start from the back, so we need to reverse each of these vectors so that we go from the back to the front of the net. And now we need our auxiliary variables. And now that we are iterating through the network from the back to the front, we can implement the formulas. So we start off with dB. dB is just the x, the previous one, so the x times the derivative of the activation function. F is the activation function, and that apostrophe right there, so this f prime is the derivative of the activation function, and it's the derivative of the activation function applied in this expression. So b plus this matrix multiplication. And so that's what we do. We say that dB is going to be, so like I said, it's going to be the x times the activation function applied to, the derivative of the activation function applied to b plus w plus dot times x. And this is dB, not x's, but x. And this is just one derivative, but we want to pack them up in a vector, so we append to the vector after enclosing the thing. Now what the formula says is we can update the x. So what's the x? The x is going to be the weight matrix transposed times dB. So it's the transpose of the weight matrix times dB. Now we don't have dB, we have all of the dBs, and the most recent one is the last item in the dBs vector. And now similarly we append something to the weights, to the vector with the derivatives of the weights. And what does the formula say? It says that a single dW is just dB times the transpose of x. So what's dB? It's the last one of the dBs plus dot times the transpose of x, I think. Yeah, exactly, the transpose of x. Now this goes through the whole network and computes all of the derivatives. Now what we need to do is we need to fix the order of these, because these are being built in reverse order. And now what we can do is we can build the network again by doing what? By taking the weights and the bias vectors and by making small adjustments. And those small adjustments are going to be exactly a small number multiplied by the derivatives. We've seen that the derivatives tell us in which direction things go up, but we want the cost function, we want the loss function to go down, so we subtract a portion of it. Now, how do we know if this is working? Well, we can do an empirical verification of this. So let's fix this, fix the whole thing, fix the script. And now what we can do is we can build some network, say a network that takes two items, then builds 5 and then 3, I don't know. And we can create a make-believe scenario. So let's pretend that there's some input that is actually going to be this column vector, and let's pretend that there's this target value which is just 3 zeros as well. And now what we do is we can take the network and feed it with a leaky rel. We can do the forward pass on the input, and now we can figure out what the actual output is, and we can compute the loss with respect to our make-believe target. So there's this target that let's pretend that we want that value, so let's compute the loss to see how badly my network is doing. So this is the value of the loss. Now supposedly if this is working, if the train operator works, by doing the assignment of the training with all of these things, so essentially if I call the dyadic operator train, then the loss should go down because I'm training the network, I'm teaching it something. So let's do that. Let's target and then the net here and then train. Now the derivatives are the activation function and the loss function, and then the input. I'm being silly. It's the activation function and the loss function, but they are called leaky relu and MSE loss. And now we got a length error, which is, well, it's a little bit annoying, but it shows you like that mistakes can happen, right? And thankfully I've already noticed what it is. So why is there a length error in here? Let me also plug my computer in because of course everything is failing at the same time. Yes, so let's not run out of battery while recording. Sorry about that. So let's take a look at DWs. So what is it? So DWs has nothing in it because its tally is 0. And for some reason it can't append this. So let's actually take a look at what this thing here is. So let me copy that and paste it in here. And it's a whole matrix. Okay, so what's the problem? Well, I don't really want to take the matrix and concatenate it to this vector. What I should do is I should make it a scalar so that I can add it to the vector. Okay, the problem is that I forgot to pack it. For example, here the dBs, that's fine because I'm taking this expression and then I'm packing it up, I'm enclosing it so that I can create a vector with those things. For example, let's take a look at dBs. See, it's packed. And so that's just the thing I forgot. I forgot to enclose here. So let me enclose. Let's fix this again. And now I can try to call this operator. And now it ran without trouble. Now if this training worked, then the loss, the value of the loss should go down a little bit. So it started off as this. Now we call the forward pass again. Now let's compare it to the value that we got. So you can see here it's 936 and now it's 934. So it went down a little bit. And we can call the training a couple more times by hand. And we can call that expression again, and you can see that now the loss went from 934 to 924. So the loss is decreasing little by little. And this shows us that the train operator is probably not terribly wrong, which is something already. So before we conclude this video, the only thing that we're going to do is remove these two silly assignments and reverse things in here. There's no need to assign them beforehand. So we can just do that. And yeah, that's essentially it for this video. I will see you next time when we start using this thing, this network that we have built, to actually do something quite interesting. Yeah, okay, so see you next time. Bye.